All right, let's take a look at the inverse functions. In this particular section, we're going to go over how to verify that one function is the inverse function of another function by using the definition of the inverse function. So f of g of x equal to x and g of f of x also equal to x. And we're also going to determine how whether a function has an inverse function, either using the definition of the inverse function or horizontal line test. We're also going to take a look at the derivative of the inverse function. So first one, let's take a look at this example. The function f of x equal to x plus 3. There are two sets. First set is 1, 2, 3, 4. The second set is set B equal to 4, 5, 6, 7. So what they try to do is, first of all, setting x equal to 1. So f of 1, which is y value at x equal to 1, equal to 1 plus 3, which is 4. That's how they end up with the first order pair 1, 4. Second order pair setting x equal to 2, f of 2 equal to 2 plus 3, that's 5. Third one, so second order pair is 2, 5. Third one, x equal to 3, f of 3 equal to 3 plus 3, which is 6. That's the order pair. Last order pair, x equal to 4, f of 4 equal to 4 plus 3, which is 7. So four order pairs are on the function f of x equal to x plus 3. So for the inverse function, you interchange or switch x and y coordinates. They end up with the order pairs on the inverse function. So 4, 1 will be located on the inverse function. 5, 2 will be located on the inverse function. 6, 3 will be located on the inverse function. Similarly, 7, 4 will be located on the inverse function. So two things I want to mention. Original function and inverse function is 1-to-1. Also, the inverse function is unique, meaning you have only one and only one inverse function. So the relationship between the original function and inverse function, the domain of the original function becomes the range of the inverse function. The range of the original function becomes the domain of the inverse function. And this is key aspect between the original function and inverse function. And in terms of definition of the inverse function, the function g of x is the inverse function of f of x if f of g of f composite of g equal to x and g composite of f also equal to x. For each x value in the domain of g and then for each x value in the domain of f. And we use this notation for inverse function using f superscript -1, that means f inverse. F inverse is the inverse function of f of x. So some important properties about the inverse function. If g of x is the inverse function of f, then f of x must be the inverse function of g. So that means it's 1 to 1. The domain of the inverse becomes the range of the original function. The range of the inverse function becomes the domain of the original function. A function may not have an inverse function, but if the function has an inverse function, then the inverse function is unique, meaning one and only one. Inverse function. You can think of the inverse function as a reverse process, or you can say that I'm doing what has been done for f of x. So let's use the definition of the inverse function to check the following. If f of x equals to x plus c, and the inverse function is x minus c. So using the definition of the inverse function, f composite of inverse. Now just replace inverse function with this one with x minus c. Now you go back to the original function, replace x with x minus c. X minus c plus c cancel c, end up with x. So verify the first condition of inverse function. Second one, f inverse composite of f of x. Now replace f of x with x plus c. Now go back to the inverse function, replace x with x plus c. So you have x plus c minus c. Cancel c, you end up with x. That's how you use the definition of the inverse function to check. Similarly, for the second example, f of x equal to c times x, and the inverse function equal to x over c. In this case, c cannot be equal to 0. So let's check f composite of inverse. So now again, keep f and replace inverse function with x over c. I'll go back to the original function f of x. Now replace x with x over c. So c times x over c. Cancel c, end up with x. Second one, condition, inverse function, composite original function. F inverse, replace f of x with c times x. Now go to the inverse function, replace x with cx. So c times x over c, cancel c, end up with x. So in that case, you check both conditions. They both equal. They both equal to x. In that case, they are inverse function of each other. And let's check these two functions. F of x equals to 2x cubed minus 1. G of x equal to cubic root of x plus 1 over 2. I want to make sure they are inverse function of each other. So you just have to check f composite of g of x. Again, using the same procedure, replace g of x with a cubic root. I have cubic root of x plus 1 over 2. Now let's go to the function f of x. Now replace x with cubic root of x plus 1 over 2. So 2 times cubic root of x plus 1 over 2 to the third power, minus 1. Now cubic root, they cancel each other. So you end up with 2 times x plus 1. X plus 1 over 2 minus 1. Once you cancel 2, they end up with the x plus 1 minus 1. Now again, you cancel 1, you end up with x. So first condition is confirmed. So now let's take a look at the second condition. G composite of f of x. So now go to keep function g. Replace f of x with 2x cubed minus 1. Now go back to the function g of x, replace x with 2x cubed minus 1. So we have cubic root. Now x becomes 2x cubed minus 1 plus 1 over 2. Now cancel 1. So I have cubic root of 2x cubed. 2, cancel 2, and cubic root of x cubed just becomes x. As you can see, we check both conditions, so these two functions are inverse functions. Just detailed solution in the background, so you take a look at it, definitely you can do that. And since we verify both condition, f composite of g equal to x, g composite of f is also equal to x, we say that they are inverse functions. And graphically speaking, this is f of x, this is g of x. As you can see, they are symmetrical with respect to y equal to x. Right? They form a mirror image. With respect to y equal to x. You can also say they are symmetrical with respect to y equal to x. Symmetrical with respect y equal to x. So let's take a look at the reflective property of inverse function. So to put in simple language, the graph of f of x contains a point a comma b, right? This is all the pair on a function f of x. Then for the inverse function, b comma a must be located on the inverse function. So if a comma b is located on f of x, which is original function, then b comma a is located on inverse function. This is one of the useful properties used very frequently. And also, the reason behind this is because these two functions are reflected or symmetrical with respect to y equal to x. That's the reason. So the x value becomes y value, and y value becomes x value. Right? And in order to prove the existence of the inverse function, we're using a test called horizontal line test. Basically, for any function, if you draw a horizontal line, they have more than one intercept, then he has no inverse function. In order to guarantee to have an inverse function, you can only have one intercept to make sure it's 1-to-1. This is just horizontal line test. Again, horizontal line test is what we use to test the existence of inverse function. The test states that a function f of x has an inverse function if and only if every horizontal line intercepts the graph of f at most once, meaning only intercept once or 0 times. For example, like the graph show, when we draw one of the horizontal line, dashed line in red, to intercept. That means it's not 1-to-1 relationship. So in this case, this function has no inverse function. Okay. In order to prove the existence of an inverse function, the function has inverse function if only if it is 1-to-1. That's why you're only allowed to have one intercept when you draw the horizontal line. And also f function f of x must be strictly monotonic. Strictly monotonic meaning it's either increasing on its entire domain or decreasing on its entire domain. It could only be either or. If those two conditions are satisfied, it is 1-to-1 and then therefore has a inverse function. So 1-to-1 and also strictly monotonic on its entire domain will guarantee to have an inverse function. And the procedure to find the inverse function, first step, switch x and y, meaning x becomes y. Y becomes x, and second step, solve for y. And third step, replace y with f inverse notation, f inverse of x. And the last step, check both conditions f composite inverse equal to x and inverse composite original function equal to x. Okay. Basically that's how you find the inverse function. Let's go back to example and let's find the inverse function. So f of x equal to square root of 2x minus 3. So based on the procedure, first of all, we write f of x as y. So now I get a y equal to square root of 2x minus 3. Now, next step, change y to x and then change x to y. Then once you do that, you solve for y. So first step, you square both sides. End up with x squared equal to square root offset each other, 2y minus 3. Now you solve for y. adding 3 from both sides of the equation. Then we get 2y equal to x squared plus 3. We'll divide 2 from both sides of the equation. So y value equal to x squared plus 3 over 2. Then again, we're going to change y, use inverse notation. So f inverse of x equal to x squared plus 3 over 2. And it's not done yet, right? It's to get a check a couple things. F composite inverse. So now replace inverse function with x squared plus 3 over 2. Then go back to original function. Replace x with x squared plus 3 over 2. So we get a square root of 2 times x squared plus 3 over 2 minus 3. Now cancel 2. X squared plus 3 minus 3. And becomes square root of x squared. And square root of x squared becomes x. Alright, so you check the first condition. Second condition, f inverse composite f of x. So now replace f of x with the square root of 2x minus 3. Now go to the inverse function, replace x with the square root of 2x plus minus 3. So we get square root of 2x minus 3 squared plus 3 over 2. Square root, again cancel each other. 2x minus 3 plus 3 over 2. Cancel 3, get 2x over 2. Cancel the 2, then becomes x. So again, second condition was satisfied. So you prove they are inverse function of each other. And the domain for the domain of inverse function is the range of original function, which is from 0 to positive infinity. Because for the inverse function, it's x squared plus 3 over 2. And the range here, x squared is greater or equal to 0. So the range of the original function is also from 0 to positive infinity based on the graph. And then the very last thing is about derivative of an inverse function. So before we talk about the derivative, let's take a look at continuity and differentiability of inverse functions. Let f of x be a function whose domain is an interval I. If f of x has an inverse function, then the following statements are true. If f of x is continuous on its domain, the inverse function is continuous on its domain. If f of x is increasing on its domain, the inverse function is increasing on its domain. If f of x is decreasing on its domain, then inverse function is decreasing on its domain. If f of x is differentiable on an interval containing c, and f prime of c is not equal to 0, meaning this is not a horizontal tangent. The inverse function is differentiable at f of c. Okay. So that means continuity, differentiability, increasing, decreasing, follow the same pattern for both original function and inverse function. And the derivative of the inverse function, the f of x be a function that's differentiable on the interval I, if f of x has inverse function g, then g of x is differentiable at any x for which f prime of g of x is not equal to 0. This g prime of x equal to 1 over f prime of g of x, just saying that for the original function at a point AB, if the slope of tangent line is m, then inverse function at a point B, A, the slope of tangent line is 1 over m, assuming m is not equal to 0. Okay, that's basically the essence of this particular theorem. So the slope of tangent line are reciprocal basically at the point, at that corresponding point. Okay. And let's take a look at this example. You can definitely see why this is true. So let f of x equal to x squared, and then x equal to x, we constrain the domain of x is just greater or equal to 0. If you look at the graph of f of x, like this, that means we only x, when x greater or equal to 0, only look at the half of the parabola, right? So that means we reach the other half. So half of the parabola. Now if you look at the half of the parabola, if you draw a horizontal line, now you have only one intercept. If you look at the function on entire domain from negative infinity to positive infinity, then it has no inverse function. So x greater or equal to 0, greater or equal to 0 will guarantee the function has inverse function, and the inverse function is radical of x. Radical of x. Try that. That's symmetrical with respect to y equal to x. So let's take a look at for the original function at point 24 and the inverse function at point 42. Show that the slopes of the graphs of original function and inverse function are reciprocals at each of the following points. A at the point 24 for the original function f prime of x equal to derivative of f of x equal to 2x using the power rule. Then in this case x equal to 2, replace x with the 2, and 2 times 2, which is 4. That means slope of tangent line at the point 24 for the original function is 4, and at the point 42 for the inverse function, f prime of inverse function, and rewrite it as x to the half. You have to write the exponent. You have to apply the first one. Let's do it slowly. First of all, rewrite the inverse function as exponential function x to the half. Now we use the power rule. A prime of inverse function. Using power rule, half goes in front, and reduce the exponents by 1. So end up with half times x to the negative half. X to the negative half becomes 1 over 2 radical of x. Flip this to the denominator, becomes x to the half. X to the half becomes square root of x. So now x value equal to 4. Replace x with 4, so you end up with 1 over 2 radical 4. Radical 4 is 2, so 1 over 2 times 2, which is a quarter. As you can see, the slope of tangent line at the 2, 4 for the original function, and slope of tangent line at 4, 2 For the inverse function, they are reciprocals. 4 1/4 is reciprocals. Similarly for b, f of x at 3, 9. So we do f prime of x, we already did it, is 2x. So now x equal to 3, replace x with 3, so we get 2 times 3, which is 6. So slope of tangent line at 3, 9 for the original function is 6. For the inverse function at 9, 3, f prime of inverse function is 1/2 radical x. Now x equal to 9, replace x with 9. It's going to 1/2 times radical 9. Radical 9 is 3, 2 times 3, which is 6, 1/6. Again, the slope of tangent line at those two corresponding points are reciprocals. That proves a theorem. In the background is a detailed solution, you can take a look at it. And when you look at the graph actually shows the relationship among them. Okay.